Up to this point, we have worked with polynomial functions, where the base contains some variable and the exponent is some integer value. What we're going to do now is look at the opposite, where the base is a number and the exponent contains a variable. We call such functions exponential functions. The major difference between a polynomial function and an exponential function is their rate of growth. If we look at these two graphs, we can see that a polynomial of degree 2 grows much slower than an exponential function with base 2. This is why pandemics and influenza can turn into a crisis, since the reproduction rate of a virus acts exponentially. For example, if someone is infected with a virus that has a reproduction rate of 2, then that person has the potential to infect 2 other people before they are cured. Now, each of these 2 people who are now infected with the virus also have the potential to infect 2 other people. This means that 4 more people will be infected, and each of them have the potential to infect 2 additional people before they get cured, which means 8 more people will get infected. This will continue further and further until, well, there's a cap in the population. This means that one person has the ability to infect hundreds or even thousands. This is why we hear on the news about flattening the curve. Essentially what they're saying is that we want the slope of this curve to be 0 after a certain point, which implies that no new cases are popping up. When we talk about the base of an exponential function, we will put restrictions on the numbers that we can use. The base can only be a number greater than 0, but not equal to 1. We do this to ensure 3 criteria are met. First, we want to ensure that our graph is continuous. This means that we want a graph without any holes or gaps in it. Second, we want to be able to put any real number value of x into our function. And lastly, we want our class of exponential functions to represent some rapid growth. See, if we let the base be a negative number, then every exponent with an even denominator will produce an undefined output. This is because it would lead us to taking the square root of a negative number. Since there are an infinite amount of numbers with an even denominator, there would be an infinite amount of holes in our graph. If we let the base be 0, then we have to restrict our domain to be greater than or equal to 0. If we let the base of 0 have an exponent less than 0, then our function can be simplified by flipping our fraction. But what's the issue here? There's a 0 in the denominator, and we can't allow that to happen. Lastly, we cannot let our base equal 1, since regardless of what our input is for x, our output would always be 1. So our function would not represent any rapid growth, but merely a constant function. Here are some characteristics of an exponential function of the form f of x equals b to the x power. An exponential function of this form will always have an output greater than 0. A graph also will always cross the y-axis at 1, so the point 0, 1 will always be on our graph. If b is greater than 1, the function will be increasing read from left to right. But if b is some number between 0 and 1, the function will be decreasing read from left to right. If you draw a horizontal line anywhere on its graph, it will intersect at only one point. In other words, it passes the horizontal line test and thus has an inverse, but that's a video for another day. Let's practice graphing some of these functions. Exponential functions can also be transformed like polynomial functions. Now we will talk about compounding interest, which is one of the few topics from pre-calc that you will use in your everyday life. If you put money in the bank and your money doubles every year, you could say that you are receiving an annual interest of 100%. Then you can create an equation that reads the accumulated amount equals the invested amount, known as the principal, times 2 raised to the t power, where t is the amount of time that has passed in years. This means if I invest $3 initially, after 1 year, I'll have $6. After 2 years, I'll have $12, and so on and so forth. What if I had an annual interest rate of 50% instead? Meaning every year I would gain another 50% of what's in my account. Then after 1 year, my accumulated value would be my initial investment plus 50% of my initial investment. I can factor out my principal amount and I'm left with this formula. So if I deposit $3 into my account, then after 1 year of investing, my account would increase to $4.50. After 2 years, my account will equal the value I had at the end of year 1 plus 50% of the value I had at the end of year 1. If I factor out the amount from the end of the first year, I can simplify my equation to my initial investment times 1 plus the interest rate raised to the second power. Thus, my ending balance at the end of year 2 will be $6.75. What if I had an annual interest rate of 20%? Then I can describe my accumulated value after 1 year as my initial investment plus 20% of my initial investment. Then after 1 year, I would have $3.60. The amount I would have after 2 years would be my year 1 ending balance plus 20% of my year 1 ending balance. After I factor and simplify, I can find my ending balance to be $4.32. After 3 years, my ending balance would be $5.18. By now, you may have noticed a pattern. We can find the accumulated amount by multiplying the initial investment by 1 plus the interest rate raised to some amount of time in years. So if we invest $100 for 5 years at an interest rate of 33% annually, after 5 years, I would have $416.16. If I were to invest $22 for 20 years at an interest rate of 2% annually, then after 20 years, I would have $32.69. If I were to invest 1 penny for 1,000 years at a 1% annual interest rate, after 1,000 years, I would have $209.59. Another thing we can do is split an annual interest rate across several months. For instance, if we wanted to split an interest rate of 20% into biannual payments, which means 2 times a year, then I can use this formula. This represents the interest rate of 20% being split into 2 payments, and this represents how many compoundings or how many times we gain interest each year. So if I had a principal investment of $2 and an annual interest rate of 20%, compounded biannually, then after 1 year, I would have $2.41. Let's compare this to the accumulated amount I would have if I were to just get one annual compounding. Notice how when I split my interest payment, I end up with more in my ending balance. Let's see what happens when I receive a quarterly compounding. All we have to do is change n to 4 and get an accumulated value of $2.43. What if I compounded monthly, meaning 12 times a year? So what can we conclude? The more compoundings per year, the more money we make. Lastly, I want to talk about what happens when we compound as many times as possible in a year. Meaning, not twice a year, not 12 times a year, but an infinite amount of times in a year. Of course, this is a hypothetical situation, but it would guarantee the largest ending balance. And it would be represented by this formula, where E stands for Euler's number, after Leonhard Euler, probably top 3 greatest mathematician of all time. His name is not phonetically pronounced, so it's not Euler, but Euler. And this number E is an irrational number, which is estimated to be 2.7182, so on and so forth. Remember, irrational numbers have no ending.